Okay, we're very happy to have Professor Chelsea Walton from Rice University, who will continue with the second lecture of Frobenius Algebras.
Okay, so last time we talked about Frobenius algebras over a field. And now what I want to do is set the basis for expanding the world or expanding the study of Frobenius algebras. Basically, I want to tell you what a modal category is. Because in lecture 3, we're going to talk about Frobenius algebras in modal categories. So just as a preview, you can form a modal category of vector spaces. You'll see it later. And Frobenius algebras in vector spaces is the same thing as a Frobenius algebra over a field. So that's how the two really connect. So I'm going to tell you what a monodal category is and give you lots of examples. I think 12 examples, but I could give you 50. Then I'm going to talk about the strip case because that's going to let me draw pictures to do computations, especially in lecture 3. Then I'm going to talk about how to move from one monodal category to another, type of functor between the two. After this, we're going to talk about when two monodal categories are going to be considered to be the same, when they're isomorphic or equivalent. All right, so that's all the setup for monodal categories. And then after that, what we're going to do is add some flavor on the monodal categories. I'm going to introduce the notion of rigidity. That's basically going to require that you have dual objects in monodal categories, nice duals. And then on the flip side, we can also talk about ratings. So again, this is types of structures that we're interested in for applications later. All right, any questions before I get started with this material? Okay, so I'm going to pick this up. Take stuff off along the way. And let's start with just what is a monodal category? What is it? Is it a category that behaves like a long way? All right, so a monodal category basically what this consists of is a category, which I'll call C, and it's going to have some extra structure on it. The monodal bit is a structure, not a property. So we're going to have a bifunctor, which I'll know with a tensor, that basically is going to combine objects, and you get an object, or combine morphisms, and you get a morphism. I'm also going to pick off a distinguished object, which I'll call 1, so that this essentially this triple behaves like a monoid. Behaves like a monoid. So monoids, you have associativity, your operation's associative, you also have your operation's unital, but we have to build that in categorically. We have to build that in. So we're going to have some natural isomorphisms. Okay, which I'm going to call A for associativity, even though I'm going to write this now, I'm never going to write it again later. I want you to see what the structure looks like. So what this is this is an isomorphism that forces associativity. So if I have a tensor Y with Z, that's going to be isomorphic to X and then tensor with Y tensor Z in a natural way. Okay, so if I swap out X with X prime through a morphism, it gets swapped out over here. I'm going to have some isomorphisms for unitality. So you have the one tensor X is isomorphic to X in a natural way, and a morphism for unitality on the right as well. Okay, so you have all this data. And you need to have some compatibility conditions amongst them. So I'll just say for this data, basically you have coherence conditions or compatibility conditions, which are usually called the pentagon and triangle axiom. I mean, basically, what the pentagon axiom is if you have 4 objects and you want to take the monodal product of them, you want to be able to place parentheses around them in any way you want. And so basically, you want all the ways of placing parentheses to be the same thing. All All right, and the triangle axiom involves these units. Okay, so that is what a monoidal category is. It's a six tuple. It's a six tuple. But later on, we're only going to work with this bit. So let me give you some examples. All right, I'm only going to write the category of the middle product in one. So if I take the category of vector spaces, let's say over C, I can take as the operation to be tensor product over C. And then what do you think the one is? The one is a vector space, and it has to be like very trivial with respect to this operation. What do you think? C, yeah. Again, this is a 4 o'clock. Are you awake? Are you awake? Okay. Now I can take the same category and put a different monoidal structure on it. And I can take the direct sum, and then one is going to be actually 0. So this is like a multiplicative monoidal category. This is like additive monoidal category. And then of course you can take different flavors of this. So I can take finite dimensional vector spaces. Finite dimensional vector spaces. So if I denote this like so, and this like so, I can do a version of finite dimensional vector spaces and multiplicatively and also additively. Okay. All right, so that's, I mean, you have lots of different monoidal categories just coming from vector spaces alone. I can also take modules over a group. So if I have G as a group, I can take as a monoidal product just tensoring over C and taking the C to be the trivial G module. So in particular here, if I have two modules over G and I tensor them, okay, what that's going to be is I take the tensor product of the underlying vector spaces, and this new action here is just given by the diagonal action. Right, so Gmod is a monoidal category. But in general, if I take an algebra A mod is not necessarily monoidal. What I need is I need some extra structure on A in order to get that the tensor product of modules is monoidal. G was very special. So the algebraic version of this is by taking what's called a bialgebra or a Hopf algebra. So if I take this to be a bialgebra, so this is an algebra that has a multiplication and a unit, but you have this map delta, which allows you to, instead of merge, allows you to break or split. And typically the way you draw or write elements under this map is you send H2, the shorthand is usually written by H1 tensor H2, instead of writing out the sum and indices and all this stuff. And then you have another map that's kind of like the inverse in a way of your unit. All right, so a category of modules over a bialgebra, this is going to be monoidal. And here, this action is just given by using a co-multiplication. And the unit is given by using the co-unit. Okay. So again, the point is that if we start with an arbitrary algebra, its category of modules is not monoidal. But if you have some extra structure on that algebra, then you can make it monoidal. And an example of a bialgebra is just a group algebra. Okay, so this is like a generalization of 5 here. Okay, any questions so far? Because I got 6 more. So there's some more interesting monoidal categories. speaking of groups, I really plainly what I can do is I can just take a group and form the category where objects are just elements of my group. Okay, in the homes, let's say a home between G and H, that's given by, well, if G is not equal to H, I'm not going to have any coefficients between them. And if G is equal to H, I can just take this to be the identity. So this is a nice, simple category. And you're going to get that this is monoidal. This is monoidal by using the group action. So G tensor H is just GH. And then 1 is just the neutral element. Right? So you can take a group and make it a monoidal category just by using the group operation. Another nice monoidal category that might come up later if you're interested is I mentioned a few times that if I have an algebra and I take its category of modules, it's not monoidal. But if you take the category by modules, it is. So if I have an algebra A and I take its category by modules, it's monoidal by taking as a monoidal product just tensoring over A and taking as a 1 the regular module. That's conditional. And then you have some, so these are all like, I mean, I'm an algebraic, so these are all very algebraic little categories involving vector spaces and groups and bi-algebras, bi-modules, etc. But of course, you can come up with like logical and topological and analytic little categories. So if I just take the category of sets, then one nice operation on it is by forming the direct product. And then here, your 1 is going to be just a singleton set, right? And another type of monoidal category that we can put on set is by taking a disjoint union, and here your neutral element is just going to be the empty set. So these are examples of what's called a Cartesian, a full Cartesian category. And then lastly, so if I start off with any category I like, any category, I can force it to be monoidal in a way. So what I can do, if I can start off with any category A, doesn't have to be monoidal, but you can make it monoidal by taking endofunctors on A. So this is like an endomorphism. This is monoidal by the little product being composition, and with the 1 just being the identity of the endofunctor. And then I'm pretty confident. And you can come up with another monoidal category by taking autocomplexes if you like as well. Those are 12 examples of monoidal categories. Are there any questions on this?
You make the algebra has to be unital, right?
Yeah, my algebras are always unital, always unital. Thank you. Yeah, thank you.
And if A is monoidal from the start, then when you apply this procedure, it gives you back A, right?
No, you still get something bigger, yeah. If it happens to be the monoidal from the start, then it's still a different category, yeah. Yeah. Thanks for asking. We're gonna see later that if you take A, B, the category of 8 modules, and we take into that, we end up getting this. This is that. Any other questions? Yes, there are.
I suppose your implicitly assume that all the category which we consider are not defined. That is the also are sets.
For rigidity? Wait.
No, it is, I mean, usually whenever I do category theory, I work with this assumption, but you're not the.
Oh, you mean like, so like any conditions on the humps, you mean?
Yeah,
Oh, no, we're not worried about linear or even abelian categories at this point. This is just a plain old category. So like that's kind of like, oh, it's a horrible category. You can still make it annoying. Yeah, so we're not assuming anything about humps. Yeah. But if we had something about humps, like linearity,
no, and the assumption is not that interested in character, interested that the odds must be set out of classes.
oh, yeah, I tend to always assume that too. So locally small.
Yeah, oh, my second question is that if we take any category and we look at example 11, is there any condition we must take to have it locally infinite in this one?
Locally finite. So
Uh,
locally finite to me means linear, it's locally small.
no, I mean, it's,
You mean locally small, like that's.
yes, sorry.
Yeah, I'm kind of varying all that, like, if this is locally small, this would be. It's okay. Okay, any other question, please, for asking? Okay, so, all right, now, what I'm gonna do is make this simpler, basically. What I'm gonna do is there's a nice way of cutting this data down. I mean, a nodal category so far is 6 people. You can really think of them as triplets. Really think of them as triples. So we say that this is all strict. Strict, basically, if these are all identity maps. All identity maps. So, the reason why we would care about this is, well, before I get to that, let's identify which categories are strict and not strict. So most of these categories on the border are not strict. Like, for instance, here I have that C tensor over C with that's isomorphic to me, not equal to me here. So this is actually technically not strict. Yeah, a lot of these are not strict. But when we come here, that's actually strict. That's nice. That's not. These two are. So you're probably thinking like, well, why would I even bother with strict monoidal categories if most of my categories are out there are not strict? But here's a nice fact. Any monoidal category is actually monoidally equivalent, and I have to define that later. But essentially, that means the same, same to a strict one. Okay, so we can think about this category of vector space as a strict category. So this is often called a strictification here. Questions?
Sorry. So I think I'm really bit unsure about why we care about this strictness. So
Oh, we care about the strictness because we don't want to do computation with these morphisms. We want to, instead of writing parentheses, we want to just be able to write x tensor y tensor z. Instead of writing 1 in x, we just want to be able to write del x.
that I can understand, but what do you mean by, let's say, this equivalent to the strict? What was the last word? Sorry, the
Strict one.
strict one.
Yes, a strict monoidal category.
Okay.
Yeah, so basically,
Ah,
that
okay.
cuts down on our computation.
I see.
Yeah.
Okay.
Thanks for asking. So once we're in the strict case, which we're always allowed to do, I'm going to show you how to do computations using graphical calculus. Ooh, don't smash fingers, don't do it. Don't do it. With graphical calculus for computations. in strict monoidal categories. Strict monoidal categories. Okay, so what's important in categories are not really the objects, but the morphisms. The morphisms are important. So often, if I want to think about X or the identity of X, I'm going to draw that just as a line here. One is so boring, I often don't even bother writing it down. And if I wanted to keep a morphism in a category, let's say F goes from X to Y, I'm going to draw this like so. So I have string colored X, and then when I go to the F box, then it becomes colored Y. And sometimes the convention is people read up, but I tend to read morphisms going down. So for example, if I have a composition of morphisms here, I'm going to have F, its color, it changes X to Y, and then G changes Y to Z. Okay. And then your tensor product, we can draw these lines side by side. So we're really going to use this type of convention in the next lecture when we work with algebraic structures.
Sorry, could you read the subtitle categorical? What is the subtitle?
Oh, graphical calculus for computations in strict limit categories. Yes. Okay. All right, so for instance, if I have like x prime goes to y, and so y prime with the f prime, I can draw this in a variety of ways. I can use this like f tensor f prime box with a string labeled x prime going down to the string y prime, but I can also write this like so. Okay, so just keep that in mind. All right. So that is what I want to say about monoidal categories. What they are, some examples of them, and how we work with them in a strict case. Now what I'm going to do is move from one monoidal category to another and talk about when they're the same. Questions? Oh, I'm going much slower than I thought. Ooh. I want to be careful, that's a problem. I'll try to keep this to an hour. Okay, so let's take strict monoidal categories. C with the data and C prime with the data. Okay, a monoidal functor. Monoidal functor. Basically going from C to C prime. This is going to be some data. Basically, this is a functor F that takes care of the category part, but it also has to place nicely with the monoidal products and the monoidal units. So you're going to have a natural transformation. Which I'll denote like so. So it's going to be natural in two objects X and Y. And basically what it does is, if you have X applied to Y, tensor X, F applied to X, tensor F applied to Y, you merge it. Okay. So this is just a natural transformation. And then you also have something that's compatible with the monoidal units. So you have a morphism, which I'll call F over naught, that goes from the 1 of C prime to F of 1 of C. And they're going to satisfy associativity and unitality conditions. Okay, so basically it just ports over the monoidal data from C to the monoidal data from C prime. Now, if. So this thing is strict. This thing is strict. If all these morphisms in the picture are identities. But that's actually quite, you know, it's a very, I don't want to, it's another word for strong, it's a very beefy condition. So oftentimes what people do is they require that these morphisms are actually isomorphisms, and in that case, we say that the monodal functor is stronger. So all these morphisms are, in this case, isomorphisms. All right, so just to note, sometimes if you read papers or books, strong is automatically imposed. So if you see the word monodal functor, sometimes you really have a natural isomorphism, and sometimes this is actually an isomorphism. So we kind of have to be careful reading from page to paper. Okay. Yeah. Let me give you one example. Oh, one example. Well, okay. So, you can talk about the action of a monodal functor on itself. The action of a monodal functor on itself. And this is how it's defined. Basically, what this is this is the strong monodal functor, which goes from C to the category, the monodal category of endofunctors on C. And what you do is you send an object X to the endomorphism given by X tensor blank. All right, so this is actually a strong monodal functor. This is the functor. And now we have to discuss what the rest of the monodal structure is. Here, this merging operation. So we're going to go from X tensor blank, composed of X tensor blank, to now XY tensor blank. Right? Now, if you actually evaluated this at Z, if we evaluate this at Z, this whole thing at Z, what we end up getting is the object X tensor Y tensor Z. So we apply Y tensor blank on Z, and then we apply X tensor blank on this. And then here we get the object XY tensor Z. So we get a morphism going from this object to this object. And what we use to define this is an inverse of this associativity factor. Okay, the not morphism is defined by using the inverse of the left ring. So this is a very natural, strong monodal functor. Likewise, we can talk about actions on the monodal categories or really any category. Any category. Okay, any questions on this? And yeah, I had a really lazy workout at the gym this morning. I feel like I'm kind of big it up now. Big it up. All right. So. You get it off. And burnt off my chicken and rice. Chicken and rice is gone. Chicken and rice is gone. Okay. All right, so now what I want to do is talk about, now that we have what a monoidal functor is, they would have from one monoidal category to another, we want to talk about when these two structures are the same. So. Okay, we have that basically, so if I have two monoidal categories, so this is monoidally isomorphic / equivalent to another monoidal category. If there exists a strong monoidal functor between them, so a strong monoidal functor between them, let's say F, and it comes equipped with this data, going from C to C prime. So that's how we port the structure going from C to C prime, but we want the underlying functor. We want the underlying functor F to be an isomorphism, or respectively an equivalence of categories. Okay, so for instance, if you have two groups and you want to know if they're isomorphic, what you do is you produce a group homomorphism that's bijective. So this is like our group homomorphism, and this is like our bijection. So let me give you one example of two monoidal categories that are pretty much the same. So if I start off with a C algebra, A, I know that its category of modules is not monoidal, but I can make it monoidal by taking the category of eigenfunctors of it. And here, the monoidal product is composition, and the one is the identity. Okay, so that's a nice monoidal category that starts with A mod. This is actually going to be monoidally equivalent, so let me use this notation. If I write that, I mean monoidally isomorphic, and if I write this, I mean monoidally equivalent. This monoidal category is monoidally equivalent to the category modules overhead. Well, here the monoidal product is given by tensor number A, and the monoidal unit is given by A. Now, how do we get the correspondence here? What we do is we take a bimodule B, and we need to send it to an endomorphism or endofunctor going from A mod to A mod. So that's going to be sent to the functor given by just B, tensor A over A blank. So this is the endofunctor going from, takes in an A module, because this is a bimodule, it spits out an A module. Right. And the monoidal structure, it uses associativity and unitality in a very natural way. Okay, are there any questions? Okay, so game against the clock. So I mentioned that if you have two structures, if you want to say that they're the same, you can basically come up with a structure where this is going from one to the other, or requiring that it's a bijection. There's an underlying set or something like this. Another way of saying that two structures are the same is if you produce two structure maps and show that they're mutually inverse. So let me give you that other way of thinking about this solution. Note, I have the two monoidal categories are isomorphic if and only if there exists some monoidal functors going from C to C prime, let's say given by F, and going from C prime to C, let's say given by G. Okay, such that we have that GF, G, first F and then G. This is actually equal to the identity monoidal functor on C, and FG is equal to the identity monoidal functor on C prime. Likewise, we have that C is monoidally equivalent to C prime if we have these types of monoidal functors such that G is actually going to be, GF is actually going to be monoidally isomorphic to the identity functor, and I have to describe what this means. And FG is going to be monoidally isomorphic. So, I mean, that's the game of category theory. Basically, the whole game of category theory is loosening up the notion of sameness. That's the whole thing. Okay, you don't want to say something that's equal as sex because that's boring, and so then you say isomorphism, and then that's boring, and then you say equivalence, and that's boring, and then that's the whole game. All right, so we're going to have that basically this monoidal equivalence is captured in this way. So what exactly does this mean? This whole two monoidal functors being the same. So for this, we have that, we have two monoidal functors. I need to talk about a monoidal natural transformation between them. Okay, respectively isomorphism. Okay, so going from, let's say, F, monoidal functor F, to a monoidal functor, I don't know, F tilde, if you will. And they're both monoidal functors that take in information in C, spit out information in C prime. So what this is this is a natural transformation, respectively isomorphism, going from the underlying functors F to F tilde, but they have to respect the monoidal structure. So I'm not correct on the diagrams, but I'm just going to say respecting monoidal structure. And of course, I have the diagram in the notes. Okay. So that we have introduced monoidal categories, how to move from one to another, some examples, and when they are the same. All this stuff is going to come up later. I'm not like just like defining the function base for fun.
In the condition of the second monoidal identities, C prime, identity of C prime.
Oh, C prime, thank you.
I mean,
Yeah. Thank you.
Also, for fun.
Yeah, thank you. Cool. All right. Any other questions, corrections? All right. So now what I want to do is talk about, duals. Do I need duals? Okay, I want to do duals really quick. Because I have to make a choice what's more important, rigidity or braiding. I think braiding is more important, so I.
Please, no, you know, it's Yes, yeah,
Yeah, because I like.
yeah, both.
Okay, well, if you gotta go, just leave. You gotta go. Okay, great, yeah, oh, that's okay. Now I can erase it, this whole board is hurt. Great. Just want to make sure I'm clear. So now what I want to do is introduce in the framework the notion of a dual object. Sometimes it's nice to have a vector space. Sometimes it's nice to work with this tool, or for tools in general. So now I'm going to talk about this notion of what's called rigidity. And it's different than I think the rigidity that you were talking about in your Zoom meeting that I was thinking. Sorry. Okay, so basically this pertains to dual objects of lessons. All right, so basically, let's fix a strict monoidal category of C. All right, and I'm going to say that a left dual of an object X and C. What this is a bunch of data. So this is an object, which I'm going to denote by X star. And what that comes equipped with is a way of evaluating and co-evaluating these two together. So you have morphisms. This is evaluation or left evaluation. It goes from X star tensor X to 1. And the way I'm going to draw this is I'm going to draw this like so. So this is an X star, this is an X, and then it just ends at 1. And then you also have a co-evaluation. So this is a map going from 1 to X star. And I'm going to draw this like so. Sometimes these are denoted by B and D for birth and death. All right, and you need compatibility. So these are called the rigidity axioms or zigzag axioms. So if I first co-evaluate and then have the identity here, and then evaluate, so this is labeled by X, this is labeled by X star, this is labeled by X. If I just straighten it up, I get the identity. And then likewise, if I evaluate here and have the identity, so this is X star, this is X, this is X star, and then evaluate, if I straighten this up, I get the identity on X. Okay. And then you also have right duals are defined in a very similar way, which are written down in the notes, but I'm never going to use them here. So usually I denote the object like so. And you have that C, the strict category is rigid if left and right duals exist for all X. Okay, let's go through some examples to make sure we really have this down. Okay, so we have our 12 examples of the monoidal categories. Some of them are rigid, some of them are not. Let's take a first basic one. Let's consider the monoidal category of just vector spaces, all vector spaces over C, tensor over C, the C. Do you think this is rigid? Do you think that every vector space has a dual?
Yes.
Okay. Let's take a vector space B, and let's suppose that it has a basis BI. Okay, let's assume that there exists a left dual. A left dual, I'll call it W. Of B. Okay, so what we're going to end up getting, all these morphisms are in vec, so we get linear maps. Our evaluation map going from W tensor over C with B, which is C, and co-evaluation map going from C to B tensor W. But what do these look like? Well, I take a vector W, tensor V, I'm just gonna write this like so. Just as evaluation. And here I'm gonna take the 1. And I have to write it as an element of this tensor product. So this gets into a sum of elements. Say BI. Little messy here. BI tensor WI. Okay, but what's important here is that the sum is finite. I need this to be well defined. Okay. So if I actually check this axiom here. So if I start off with V, it's isomorphic to C tensor over C with V, I'm supposed to co-evaluate. Okay, so I landed V tensor W tensor V, and then I evaluate in the second slot. And then here, I want that to be the identity. Required that that's the identity on V. But if I actually go through and take a vector V and trace it all the way through, so I get VI tensor WI tensor V. And let's suppose that I write V as like, I don't know, something over J, going from 1 to M, and M has to be finite as well. I mean, I need these all to be nicely well defined. Okay. Then what I end up getting here is I sum over I go from 1 to N, J going from 1 to M, and I get lambda J, VI, WI evaluated at VJ. But this is in C. And this is in C. So this whole thing is in a finite dimensional vector space. So basically what I get is that the dimension of the image of this map is finite. So that's forcing me to be finite dimensional. Okay, so rigidity is really tied to finite dimensionality. And again, if you go to papers and books and stuff that mention like tensor categories, things like this, they might write V or vec, but really what they mean by this category is finite dimensional vector spaces. Unless it's like bold or underlined or something. That's a sneaky thing. It's a sneaky thing. So really we need finite dimensionality. Okay, so give us some other examples of that. Here. Okay, so not rigid. Add back column. Okay, rigid. Good column. All right. This is in the back column. That manure category is not rigid, but if I just tweak it a bit, maybe finite dimensional, then it becomes nice. It has duals. This is in the back column. Modules. If I forget the G action, I end up with vector spaces. No duals. Not good. Then if I just tweak it a bit, it's good. My goodness, that's so nice. Same thing with all algebras. Bad. Good. Bad good. Okay. Now, what if I take an algebra and I don't want to just take bimodules because we know that in dimensional, we might want to say models. What if I take finite dimensional bimodules? Well, in general, this is bad. It's not rigid in general. In general. So for example, if I take one of our favorite algebras from the first lecture, this category is not rigid. But if I take this category of finite dimensional bimodules for now, this is finite dimensional and semi-simple, then it becomes fluid. Then we have rigidity. Okay. So like, group algebra is easy. All right. So, that is what rigidity means. Basically, you have duals. So you might wonder, like, okay, rigidity. Is there such thing as like a rigid monoidal functor? And the answer is, well, rigidity is like, it's like a property. There exist duals. These either exist or they don't. And typically, if you want to add an adjective on a functor, what you're doing is you're asking to preserve structure. You're asking to preserve structure. Like, we don't talk about the abelian group homomorphisms. We just have group homomorphisms between abelian groups. So we don't talk about rigid monoidal categories. But really briefly, I will say that strong monoidal functors send dual objects to dual objects. And the purpose of those. Trying to shape some minutes. Now, here's another interesting fact that I really like. It pertains to this setup, actually. Here's a nice fact. If I have basically some monoidal categories, C and C prime, C and C prime, and I have two monoidal functors between them, F, and let's say up tilde. Okay, and I have this nice monoidal natural transformation. So this is the monoidal natural transformation. Okay, so if I'm given that, if we get that the source is rigid, if this is rigid, then what we see that monoidal natural transformation is automatically a monoidal naturalized. So by imposing rigidity here, any natural transformation becomes a natural isomorphism. So kind of repackaging this in a different way, if I were to take the category of monoidal functors going from C to C prime. So objects are monoidal functors, and maps are monoidal natural transformations. In this category, any morphism is an isomorphism. Any morphism is an isomorphism. In other words, this category ends up being fluid. Maps are isomorphs, always. Any questions on this? Rigidity actually buys you a lot. We're going to let you know. You're going to see groupoids tomorrow with Frobenius algebras as well. Okay, this is all not an accident. Questions?
Sure, I just missed that about C, the rigid and C prime.
C prime is anything, yeah, it could just be a monoidal category. So yeah, if this is rigid, then this ends up being a groupoid. Any map is an isomorphism.
Mean C and C prime have no equivalent each other. If C is rigid, C prime has.
Oh, no, so basically what we do is we fix C and C prime, they're fixed, and we take the collection of natural transformations between two maps. So the objects here are the maps. So C and C prime are fixed, the objects here are the maps, and the maps are now the natural transformations.
Yeah, but the question is the rigid property is that what can happen then?
Oh,
I guess not.
yeah, duals still duals. In a way, yeah, and that could be the
But I know a fact is that the monoidal equivalence other than preserve the dimension of the magnetic space.
equivalence doesn't preserve the illusion of that.
Yes,
Yeah.
now if, then the question is to preserve the duality, then, but. I think, yes.
I'm sure the question.
Isn't that the consequence of the theorem that you stated, that Chelsea stated that strong monoidal functors always map duals to duals?
Yeah, it's
I
good.
think everything follows from that.
Strong enough fungus and duals and duals. I didn't write it on.
Everything follows from that.
Yeah.
Which is just by checking the sequence, like if you have one set of x, then you want to say that.
Okay. Right, I think I can blast through this in 5 minutes. Now what I want to do is, again, this is like, sorry, this is almost like all of my one in one lecture. I'm just squeezing this in. Now what I want to do is talk about gradients. Let's talk about gradients. Okay, so this is a different flavor of virginity. Again, it's like, basically, what happens is you have some like physical thing or topological thing, and you want to model it in the category. Sometimes you need some extra structure on a category for an accurate model. The rules are nice if you have, rigidity is nice if you have dual objects. Grading is going to be nice if you want to be able to swap across the tensor product. Okay, so this is going to be an extra structure as opposed to a property. So, okay, so we have that. I'm going to work in the strip case. This is graded. This is going to be extra structure if it is equipped. If it is equipped with a natural isomorphism, which I'll call C, that'll be natural X and Y. And what that's going to allow us to do is take X tensor Y and very naturally send it to Y tensor X. Okay. And the graphical calculus for this. So I have X, Y being sent to Y, X. Typically, I write this like so. Okay. And this has to play nicely with the monoidal product. So what we get is that if I swap X tensor Y over Z, that's going to be the same thing as swapping Y over Z into X over Z. And then likewise, we have this picture. All right. And this is the metric. And further, this is symmetric. If we write it twice and we get the identity. So swapping X over Y and Y over X is the same thing as doing nothing. And in this case, typically what we do is we write the C as just the crossing. So some examples. We have that. If I have my middle category of vector spaces, then just flipping, the usual flipping across the tensor product is symmetry. Okay. Same thing with G models. Has a nice symmetry. Same thing. And if you wanted to spice this up and look at like just a Hopf algebra or a algebra or something like that, then basically what you get is that the C corresponds to, I would say, just action an R matrix. But again, the details are in the notes. All right, so that's what a graded monoidal category is. How do you move from one to another? So we have that a graded, respectively symmetric monoidal functor. A graded, respectively symmetric monoidal functor, going from one graded, respectively monoidal category C to another one C prime. This is going to be a monoidal functor that respects the gradient. So this is going to be actually a strong monoidal functor. F along with the data, so that the gradient is respected. So for instance, if I were to take two objects X and Y and then merge them with an F2, and then apply the gradient inside, so I intersect F of Y tends to S. That's the same thing as first applying the gradient on the outside, and then merging. So you want that technique. All right, so I'm not going to give examples of these types of functors because the most important example of a symmetric monoidal functor is going to come in lecture 4. This is what a TQFT is. It's a special type of symmetric monoidal functor. Okay, so with that ends. Should have ended on time. I did it. I did it. I did it in an hour. What the winner? Yeah, done. Anyway, yeah, that covers all the material, all the background materials you need for the
Questions?
I did it, but can you read it? And that's another. So,
I have a philosophical question.
sure, I like those.
In this pictorial representation of the gradient, does it reveal something deep at some level, or is it just for convenience? Just for writing?
Well, it is for convenience, but yeah, it does represent like grades. So when you do like actual grades in topology, so like these types of moves here, I'm pulling these strings apart and recovering this. There's something much deeper going on.
Yeah, because it actually it makes our life much harder with all these pictures.
Yeah.
Because it's not really convenient, but
Oh, actually, it makes my life easier. Because if you want to show that two morphisms are the same, right? You can go through it line by line in this string of this composition of morphisms.
I can recognize it easier.
Yeah,
I can see.
yeah, otherwise you can do basically trying to have like, you have a long string of composition of morphisms, one to another. You do it line by line equationally. You use commutative diagrams, or you can use pictures. And sometimes the pictures give you a little bit more intuition.
So
But they're for the type.
so they're deep, really deep.
Yeah. Especially for naturality. Usually naturality, you kind of have to write out line by line, but this one, I just say, okay, I can do this stuff. And it makes things easier.
Questions?
This is just basically almost notation. Like, is there any reason why I should put, let's say, 2 and 0 on inside the parentheses?
Oh, thank you for that question. So there are lots of different notations. Sometimes people don't do the parentheses, sometimes people do subscripts.
Yeah.
Sometimes people do an F in a row in a different letter, like, yeah, so, but the 2 and the 0, I mean, essentially the 0 is, the 0 pertains to the 1, and the 1 is kind of the boring bit. You're preserving the monoidal unit, so you're kind of the 0 bit. And if you just has to do with like preserving in a way multiplication. Yeah.
It's kind of like the number of arguments.
Yeah.
But yeah, if for the set, for FIDO, we have one which is fixed, so you have no argument.
Yes, yes. So, yeah, I mean, there's this thing called a conoidal functor, where you just go the other direction and break. And then I will put like subscripts over the two zeros.
Other questions? Let's thank Chelsea for that.